All right, strap in everyone, because today we are diving deep into some pretty mind-bending stuff. Bell's theorem. Get ready to have your philosophical assumptions challenged, because we're going to explore how a theorem about probability distributions ends up shaking the foundations of physics A&D philosophy. And to help us unpack all of this, we're turning to the Stanford Encyclopedia of Philosophy's entry on, you guessed it, Bell's theorem.
You know, what's always fascinated me about Bell's theorem is that it grapples with a question that's plagued philosophers for centuries. Can we explain reality without resorting to, as Einstein put it, spooky action at a distance? You know, that idea that something happening over here can instantly affect something way over there faster than the speed of light? It's enough to give anyone a headache.
Yeah, that's definitely getting into the nature of cause and effect, the kind of stuff philosophers love to debate for hours on end. But how does this theorem even begin to address something like that?
Well, it all starts with this idea that maybe, just maybe, quantum mechanics isn't the whole picture. Maybe there are these hidden variables, like extra information we just haven't discovered yet, that are actually determining the outcomes of quantum events.
So kind of like, imagine we have two spinning wheels, each divided into red and blue segments, and when you spin them, they seem to land on a random color each time, right?
Right. But if there were hidden variables at play, it would be like those wheels were rigged with these tiny gears predetermining the outcome, even though it looks random to us.
Oh, I see. So the hidden variables are like the puppet master behind the scenes, pulling the strings and making things happen the way they do.
Precisely. And that was the hope of something called the Hidden Variables Program, to kind of complete quantum mechanics and restore a sense of order to this seemingly random world. But here's the thing. Early attempts to prove that hidden variables couldn't exist, like something called the Bell-Cochen-Specker theorem, they relied on this assumption called non-contextuality.
Non-contextuality. Okay, you're going to have to break that one down for me.
Sure. It's basically the idea that a particle's properties, like whether our spinning wheel lands on red or blue, exist independently of how they are measured. You see, Bell, he argued against that. He suggested that maybe the act of measurement itself is playing a role in defining reality.
Whoa, okay, so we're already getting into some pretty deep philosophical territory here.
Yeah, we are, and it gets even wilder.
Okay, so where does Bell's theorem itself fit into all of this? I mean, how does it connect to hidden variables and non-contextuality and all of that?
Well, you see, Bell, he was a bit skeptical of these early no-go theorems for hidden variables. He thought if we were going to rule them out, we needed a more general approach, one that didn't rely on such strong assumptions like non-contextuality.
So he wanted a more foolproof way to test the idea of hidden variables, something that wouldn't be tripped up by these tricky philosophical assumptions.
Exactly. And that's where Bell's theorem comes in. He set out to derive an inequality that must be true, IF locality holds, regardless of the specifics of your hidden variable theory.
Okay, so just to make sure I'm following, if something happening here can't instantly affect something over there, then this inequality has to hold true no matter what kind of hidden variables you might have.
You got it. And here's where things get really interesting. For both physicists and philosophers, quantum mechanics, the theory that's been wildly successful in predicting experimental results, actually predicts violations of Bell's inequality.
Wait, hold on. So if quantum mechanics is right, then either locality is wrong or hidden variables are wrong, or maybe both. That's kind of a huge deal. I mean, does this mean we have to throw out our intuitions about cause and effect?
Well, that is the million-dollar question, and to see if this violation actually happens, we need to delve into the world of experimental physics, and that is for next time.
Okay, so last time we ended on this cliffhanger. Does quantum mechanics actually violate Bell's inequality out there in the real world? Like, is this just a theoretical curiosity, or does it have actual experimental teeth?
Right, and that's where things get really interesting. Because to see if this theoretical prediction actually held up in the messy world of experiments, physicists had to get creative.
Yeah, I bet it wasn't easy to test something as abstract as Bell's inequality.
Yeah.
I mean, how do you even begin to design an experiment to prove or disprove something like that?
Yeah, for decades, they grappled with designing these experiments that were precise enough and sensitive enough to test Bell's inequality. And it wasn't straightforward. Many of the early results, they could be explained away by various loopholes in the experiments.
Loopholes? What do you mean?
Imagine you're trying to test if two people can communicate telepathically, right? You put them in separate rooms, ask them questions, see if their answers match up. But what if there's a tiny hole in the wall and they're secretly signaling each other? That hole, that's a loophole in your experiment. It could lead you to think they have telepathy when really it's just sneaky communication.
I see. So in the case of Bell's theorem, These loopholes meant that hidden variables might still be at play, even if the results seemed to violate the inequality.
Exactly. One of the biggest challenges was something called the communication loophole. If the entangled particles, no matter how far apart, could somehow signal each other during the experiment, even at the speed of light, then hidden variables could exploit that to fake a violation of Bell's inequality.
So they had to make sure those particles were truly isolated, like no chance of them whispering secrets to each other, even at light speed.
Right. They had to be super clever in designing these experiments to close off all these potential backdoors for hidden variables to sneak through. One groundbreaking experiment by Elaine Aspect and his team back in the 1980s used these rapidly switching polarizers.
Rapidly switching what now?
Polarizers, think of them like filters that change how they measure the properties of the entangled particles, and they switch faster than the time it takes light to travel between them.
Whoa, so they essentially outmaneuvered the speed of light to rule out any sneaky signals between those entangled particles.
Precisely. But that's not all. There was also the detection loophole. You see, experiments often use photons, which are particles of light. But not all photons emitted are detected. What if the hidden variables were somehow influencing which photons were detected and which ones weren't?
Huh. I guess if you're only recording certain answers to your telepathy test, the ones that fit the hidden variable theory, it's going to look like telepathy is real, even if it's not.
You're getting it. And to address that, physicists had to develop incredibly sensitive detectors that could register nearly every particle, and they came up with new inequalities that were less vulnerable to this loophole.
Wow, so they were really working hard to close all these loopholes and get to the bottom of whether Bell's inequality was truly being violated.
Oh, yeah. And all this effort led to something truly remarkable, a series of what are called loophole-free experiments in 2015.
Loophole-free, meaning they finally shut down all those sneaky ways for hidden variables to mess with the results.
Exactly. These experiments, they used a variety of entangled systems and these incredibly sophisticated setups, and they all overwhelmingly demonstrated that Bell's inequality is indeed violated in the real world. The correlations between those entangled particles were stronger than any local hidden variable theory could allow.
So does this mean the universe is officially spooky? Like we have to accept this spooky action at a distance that Einstein was so skeptical of?
Well, not necessarily. Remember, Bell's theorem doesn't tell us why the inequality is violated, only that it is. It's like a detective finding a broken vase at a crime scene. It proves that something happened, but it doesn't tell you who did it.
That's a good point. So if rejecting locality isn't our only option, what other explanations are on the table?
That's a great question, and that's something that we will delve into next time when we continue exploring the philosophical rabbit hole of Bell's theorem and its implications for our understanding of reality.
Okay, so we've gone down this rabbit hole, and it seems like the universe is playing by some pretty strange rules. Rules that really defy our everyday notions of cause and effect. I
Yeah.
mean, where do we even go from here? Like, what are the possible ways to make sense of these, let's be honest, mind-bending findings?
This is where I think your philosophical expertise is really going to come in handy because the violation of Bell's inequality, it's like it opens up this Pandora's box of philosophical interpretations.
Lay it on me. I am ready to have my reality completely shaken up.
Well, one path is to just kind of bite the bullet and accept non-locality, to embrace the idea that there are these genuine, faster-than-light connections in the universe. And the Stanford Encyclopedia entry, it points out that this really challenges our understanding of special relativity.
I mean, that's a tough pill to swallow.
Yeah.
It's almost like saying the universe has these secret tunnels that let things bypass the speed limit of reality.
It definitely stretches our understanding of physics, that's for sure. But some folks, they argue that maybe we're just clinging too tightly to our classical notions of space and time. Maybe at the quantum level, distance itself is an illusion.
Okay, so instead of things influencing each other across these vast distances, maybe it's more like they're entangled in this deeper way that transcends our usual conceptions of space.
Exactly. That's one way to think about it. Another option, and this one's even more radical, is retrocausality. The idea that effects can actually precede causes, that our measurements in the present can somehow influence the past.
Okay, now that sounds like we are getting into some serious science fiction territory here. Are there any serious physicists or philosophers who actually entertain that idea?
You might be surprised. Hugh Price, he's a philosopher at Cambridge. He argues that retrocausality, it might actually offer a more symmetrical and elegant way to understand these quantum correlations. It's like saying that the two spinning wheels we were talking about earlier, they weren't just pre-programmed to land on certain colors, but that the very act of observing the color of one wheel somehow influenced the color the other wheel landed on in the past.
Oh, my brain is doing backflips just trying to wrap itself around that one. Are there any interpretations that are a little less, well, mind-blowing?
Well, there's always superdeterminism. This one basically says that everything in the universe is predetermined from the Big Bang onward. Like, no free will, no chance, just a cosmic script that's playing out exactly as planned.
So in this view, it's not that the particles are mysteriously connected or anything. It's more like their fates were sealed billions of years ago, right at the beginning. Like those spinning wheels, they were set in motion at the dawn of time, and their final colors were inevitable.
Exactly. It's a way to preserve locality, but, and it's a big but, at the expense of some pretty fundamental assumptions about choice and agency.
Yeah, I can see how that interpretation might be a bit tough to swallow for some.
Mhm.
What about the many worlds interpretation? That one always seems to pop up in discussions about quantum mechanics.
Ah, yes, the many worlds interpretation. This one suggests that every possible outcome of a quantum measurement actually happens, but in different branching universes. So there's no spooky action at a distance because everything that can happen does happen, just not in our particular branch of reality.
Hold on, so you're saying that there's a parallel universe out there where I'm having this exact conversation, but I'm wearing a clown suit?
It's entirely possible. The many worlds interpretation, it offers this way to preserve the completeness of quantum mechanics without resorting to non-locality or retrocausality. But it comes with its own baggage, a whole infinite multiverse worth of baggage.
Okay, so we've got this whole buffet of interpretations,
Yeah.
each with its own, philosophical baggage. Is there any consensus on which one is the correct one?
Sadly, no. Bell's theorem, it doesn't give us a neat and tidy answer. It's more like it reveals this crack in the foundation of our classical worldview. And each of these interpretations, it's like an attempt to patch that crack in a different way.
So we're kind of left with more questions than answers. Does that mean all this head-spinning theorizing was for nothing?
Not at all. Bell's theorem has completely revolutionized our understanding of the universe. I mean, it's spurred some incredible advancements in fields like quantum computing and cryptography. And more importantly, it's this testament to the power of human curiosity, our relentless drive to understand the world around us, even when it means confronting some truly mind-boggling ideas.
It's like we've stumbled upon this hidden door leading to a realm of possibilities we never even imagined before. And even though we might not know what lies beyond that door, the very act of opening it has expanded our horizons, well, immeasurably.
Well said. Bell's theorem, it challenges us to rethink some of our most cherished assumptions about reality, about cause and effect, the nature of space and time, and even about the limits of human knowledge. It's this reminder that the universe is far more complex and mysterious than we tend to give it credit for.
Well, this has been one wild ride. And to our philosopher listener out there, if Bell's theorem has taught us anything, it's that the search for truth, it's an ongoing journey, full of unexpected twists and turns. So don't be afraid to question your assumptions, embrace the unknown, and always keep exploring.
And who knows? Maybe someday you'll be the one to crack the code of the quantum universe and provide the next mind-blowing interpretation that completely redefines our understanding of reality.